start up the show, then we will do the interview, and then I'll say thank you, and then you're free to close the window and head off.
Okay.
And we are now theoretically live.
Okay.
This is all theoretical.
Yeah, it's all theoretical. Actually, my
We're in
audio is...
hypothetical space right now.
Yeah.
Okay.
In the end, everything is.
Good.
Yeah. Hold on. My audio is so low.
It is. Can you move your microphone closer to you?
It's not that.
Oh.
You're having trouble hearing me, though?
Better. Well, it's just you're much quieter than the other people who are talking.
Yeah. And so
I don't know how I sound comparatively.
Now I'm probably a little louder, actually. Okay. All right. People will have to tell me if it's the right volume.
Let us know what you think.
Let us know. Hey, everyone. All right. Now's your chance to say hello to us before the show begins.
Welcome to our crazy.
What? No.
No.
Kidding?
Welcome to an awesome hour of my week.
I'm really excited. Actually, this is going to be great. Did anyone see this really interesting TED Talk that was given by Scott Solomon, about the evolutionary biology on Mars and how humans will change if they're on Mars?
I saw very briefly something about how it will take a much shorter time than we ever thought it would for humans to become completely different than Earth humans.
Yeah, and the takeaways are we will become nearsighted, or the humans there will become nearsighted because they're going to live
way
underground.
Ahead of you.
What's that?
Way ahead.
Yeah, you're way ahead. Yeah, you're ready to go because they're going to live underground. They're going to live in tunnels. So they'll be nearsighted. They will get denser bones. Sorry, they will have lighter bones, and so it could lead to complications like fractured pelvis during childbirth. They'll get a different skin tone because of the higher levels of radiation. They'll use oxygen more efficiently, and they will lose their immune system, so they can never come back home to Earth. And any humans connecting to them would be deadly. So
wow, that's a pretty picture, isn't it?
I know. And in fact, there was a book, there was a story, like in the 1950s or something like that, where, and I forget the science fiction writer, like Paul Anderson or something like that, where he was saying that he was pointing to these graves on the moon, that the first colonists on the moon, it was because people weren't careful, and so children were born on the moon. And they were all 6 feet tall, but they were the children because they just kept growing. They wouldn't stop growing in the lower gravity. So.
No, thank you.
Yeah, I know.
That does not sound good.
My point is, and we'll get to
this. There have been
times
when I've wanted to be 6 feet tall, but not for that reason.
Yeah, my point is we have to, and this is why I'm looking forward to this conversation today. This is going to be fun. All right, I'm going to say hi to Annie Wilson, Astro B, Avi Scott and Flower, Ben Kalo, Bob Mueller, Christian Woodland, Cyrilio, David Dunn, David Fairweather, Frank Tippin, Giselle Sabrin, Gordon Dewis, Ian Farkaron, Jay Alexanderson, John Musk, John Victor, Kyle Carmichael, Larry Beckham, Michael Collins, Nancy Graziano, Neil Yoon, Nightbot, Paranor, Rick Schwartz, Scott Bragdon, Sergusi, Spencer Smolinski, Von Lichtenbutz, William Hutchings, and Zapfin. Hey, everybody. Welcome to the Weekly Space Hangout. Let's get into the show. I think we're about across the 5-minute mark. So let me just put everyone back into their boxes.
Everybody to their corners.
Everyone to their corners. Back to me. Here we go. Hello and welcome to the Weekly Space Hangout for May 22nd, 2019. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about the moon threw up its guts onto the surface, plutonium from neutron stars, maybe an update on Artemis. Something interesting happened this week. Shout out to Eric Berger of Ars Technica again. Solar system protected wilderness, new Earth-sized planets discovered, and once again, we have no idea how old the universe is for real. Joining me this week, we've got, Dr. Kimberly Cartier. Kimberly, welcome, as always, to Weekly Space Hangout.
Hey, Fraser. Happy podcast day.
And
the
thanks
best day of the week.
Thanks for coming back. We missed you.
Yes, thank you for excusing my absence last week. I was under a tight deadline at work, writing lots of awesome articles.
And our trained astrophysicist is still out in the wild, but we brought in a replacement this week. We've got Dr. Brian Koberlein. Brian,
Hi.
welcome back.
Thank you. It's been so long that I think the last time I was on, Google Plus was still a thing.
So sad.
That is a long time ago.
Yeah.
All right, we're going to get into the stories shortly. Before we do, I would like to give a big shout out to our good friends at the Weekly Space Hangout crew. They are, of course, the fans, the executive producers, and if you want to be a part of the community, I highly recommend go to wshcrew.space, and you will be able to find out more. They will sign you up. They will give you access to the Slack chat that's going on in the show right now. They will give you access to they'll give you your executive producer card, and of course we got that this week, another guest that's amazing, and I had nothing to do with it. So if you want to be part of this, especially like Surprising Fraser with awesome guests, then you should become a member of the Weekly Space Hangout crew. Totally free, and they will help you sort of maintain your sanity during the dark times as we go through the summer hiatus. So wshcrew.space, especially without Google Plus. Now there's like nowhere that you can go and maintain connection with all these wonderful people. WSH Crew. They'll set you up. All right, let's get into this week's guest. We've got Dr. Suze Bailey from Colorado State University. Dr. Bailey, welcome to the Weekly Space Hangout.
Thank you. Thank you very much for having me.
All right, so the question I always like to ask people, who are you and what do you do?
I am Susan Bailey, and I'm a professor of radiation biology at Colorado State University.
And I mean, the part that I think is going to be very exciting for me, especially, and everyone watching, is that you were involved in NASA's twin study. You sent one astronaut to space, and his twin brother got to remain down here on Earth, and you got to track the changes.
That's correct. So yes, I was one of the principal investigators on the NASA twin study. We were interested in looking at the question of aging. So looking at our monitoring telomere length and telomerase activity in both of the twins.
And I mean, we have heard everything from nothing really happened, don't panic, to Scott Kelly's genes went crazy and he's a monster now.
I know. He's a space mutant.
He's a space mutant, and he will never be the same. So let's talk about the experiment first, and then we can talk about the results. So how did this all play out?
So it's really a very interesting story because NASA selected Scott Kelly for their first one-year mission. And it was actually after that Scott Kelly himself, during a press conference, asked NASA, well, are you doing anything particular because I have an identical twin brother, Mark Kelly, and like, wow, we were both, astronauts. We were both Navy test pilots. We're identical twins. It seems like that you should be doing something. And of course, the first answer was, no, we're not doing anything. And the second answer was, oh my gosh, we better hurry up and do something. So they very quickly put together a call for research proposals. And we submitted one, as did many, many others across the country. And we're fortunate enough to be selected as one of the 10 that then eventually became known as the twin study.
So this was their idea?
It really was. It came from Scott originally. I mean, that was the very first part of it that said, well, what about my twin brother?
Yeah. That is really convenient that he had that sort of,
Yeah.
you could
And
bring
so
that
it
to
when
the
and
table.
it wasn't just that they were identically, genetically identical as twins, but they also had very similar lifestyles. So they had both been astronauts and Navy test pilots, all these things that we associate with similar lifestyles. So they were similar in both nature and nurture, which is a classic question, which one really influences things more. But you couldn't ask for a better science experiment, that you have these two individuals as closely matched as you can possibly have, one of them spending almost a year in space and the other one spending his that same period of time on Earth living a very normal kind of Earth life in Arizona.
Right. And so then you took regular samples from them?
That's right. That's right. So the study started probably about 6 months before he went up on the mission, and then went throughout the 1 year mission, and then about 6 to 9 months afterwards. So we had samples for our particular study, blood samples, before, during, and after the 1 year mission from both Scott and Mark. And that just by itself is a remarkable accomplishment. Getting them from both of them at pretty much the same times.
One in space, one on the ground. Yeah.
Exactly.
Um,
Yeah.
okay. And so then you and many other researchers got a chance to analyze, like, did you map their entire genome?
Well, some of the studies did, yes. They sequenced DNA, they sequenced RNA, they looked at the epigenome, or all the modifications that can happen to the DNA or the RNA. There were studies that looked at the immune response. So, for example, they each gave themselves a flu shot before, during, and after. And, was the response any different in space? There was a team that looked at the microbiome. There was a team that looked at proteomics, metabolomics, and then there were some behavioral endpoints as well. So there was a behavioral cognition study where both of them took cognition tests throughout, before, during, and after. And then, there was ours that looked at telomere length.
Uh, and so what were, I guess, the most interesting, biggest differences that you found?
So for our study particularly, I mean, I think, we certainly went into the whole thing hypothesizing or thinking that in fact Scott's telomeres certainly would shorten more rapidly than Mark's, because telomeres they're the ends of our chromosomes. They help protect the DNA, the chromosomes, from damage. They also shorten as we get older. Every time our cells divide, telomeres shorten. And as well as they shorten even with all kinds of different life stresses. So even just, things that you associate with everyday life here on Earth, certainly the stresses they have in space, like, isolation and physical stress that they're under, as well as nutritional. They eat space food every day
Yeah.
and they don't like it very much. So they all lose weight. And, so, surely all of that stuff would amount to Scott's telomeres shortening more rapidly than Mark's on Earth. And so that's what we proposed going into the study. And of course, as science is, we found exactly the opposite thing.
Right.
That's why you do the experiment, that in fact Scott's telomeres were longer at every single time point that we had during his time on the International Space Station. So that kind of brings up the whole thing about, aging, of course, and maybe if you've seen Interstellar, he came back younger, he didn't age. And so I don't think it's really related to any of that, but I'm not sure what it is related to either.
I don't think, though, it was the fact that Scott spent a lot of time near a supermassive black hole experiencing time dilation. I think that was
No, I don't either.
I think that was a contribution in Interstellar as opposed to being in space.
Yeah, and they're on the space station, which is in low Earth orbit. It's not traveling, at the speed of light, any of those things. So, I mean, it would just be milliseconds, if anything. So it's not that. It's something else, and we just don't know what it is.
Now, we've got a question here from Kevin N, and I actually have no idea what he's asking, but maybe you will understand. He says, does the
Okay.
study include isotope intake or monoclonal antibodies or other markers given in orbit or here to compare? Would it be of value for imaging comparisons in orbit versus on ground if possible? Did that make any sense? Isotope intake
Wow.
or
So
monoclonal antibodies?
imaging, like medical imaging, I think is what he's talking about. Um, I don't think that it would, but again, I one of the really important things I think moving forward is that they are increasing the capabilities on the International Space Station all the time. So because it is a national laboratory, it is designated as a national laboratory. It is very limited because of space and all kinds of things. But as we get more capabilities, that something like that might be possible. But I'm not sure that it would really help us understand the telomere result.
Um, from Nancy Nancy Graziano wants to know, do you anticipate any long-term impact on Scott that may not manifest itself for 1, 2, or 3 more years down the road? How long will Scott and Mark be monitored for any differences?
That's an excellent question, and certainly one that I've been very concerned about, because I think that is the important thing here, is that we're learning things from the twin study that we should be looking at, monitoring, keeping track of our astronauts, not only during space flight, but also after they return. So there are things like cardiovascular disease, for example, and cancer, even more long term, that could be consequences of the radiation exposure, or whatever it is, that is going on there. So I think obviously, as we look at the telomere results as a measure of aging, but also as a measure of the risk associated with age-related diseases, that we just need to keep a much better eye on our astronauts and keep monitoring them over the years after they return.
I mean, do you think that you are able to provide any practical suggestions, both back to NASA and to the way astronauts spend their time in space? Change their macros, lift more. Is there anything they can do to, change their telomeres?
Yeah, so that's got a lot in that question. So certainly we know that on the space station they exercise a lot because they have to combat the muscle loss and bone loss and all of that. They do that. They have a very defined diet. They lose weight. Scott lost about 15 pounds while he was up there, again, mostly because they don't like the food very well. So, and they're exercising and they're busy, all the time. So things that we associate a lot with healthy lifestyles: caloric restriction, exercise. They don't get a lot of alcohol, and they shouldn't get any, but who knows? The Russians are also up there. So
Yeah.
I think there's vodka up there for sure. But so things that we really do associate with healthy lifestyles are a part of the whole thing. But in the end, I think what we have to really do is understand more about why telomeres are longer or staying longer in space than they are on Earth. And once we understand that, is it radiation exposure? Is it microgravity? Is it what changing
Right.
in cell population? Once we understand that, I think we will be able to answer that question a lot better.
But there is a possibility in your mind that it could just be the healthy living from
There
being
is
on
that
board the
possibility. There
space
really
station.
is.
Yeah.
Yeah. Because things like that, and just some of the nutrients have all and exercise, all these things have been associated with maintaining telomere length better here on Earth. But really and truly, none of them have been associated with getting longer telomeres. So that's really going to be our challenge going forward.
So speaking of going forward, I mean, as we've all heard, the next big plan is to build the gateway, send humans back to the surface of the moon.
Mhm.
Uh, wouldn't it be great to have Scott, Kelly, or maybe Mark this time, whatever, go and spend a year on the Gateway and find out what happens to a human being of a year, say, in deep space?
Oh, definitely. Because I mean, the only time, honestly, that any humans have ever been outside of the protection of the Earth, the atmosphere, the magnetosphere, is our Apollo astronauts. They are the only ones. And they only spent, 6, 7, 10, 12 days on outside of that protection. So, we really don't know much about what the health effects of that are. And certainly I think, Scott's been asked, would he go to the moon? Would he go to Mars? And he says, sign me up.
Yeah, of course he does.
You
Yeah.
know? Yeah, but he did retire the minute he got back too.
Yeah.
So
But he still says, sign me up. He'll come
he
out of
does.
retirement for that.
Put me in coach.
So, I mean, like on the one hand, you're seeing, NASA is doing a very conservative, very careful approach to this. This is a wonderful study to get at some of these questions. And yet, on the other hand, you've got SpaceX and various groups looking to colonize Mars as soon as humanly possible. Where do you stand on is it even safe to do that yet?
Yeah, I mean, that's again, I don't know that we really have the answer to that. I think, as our technology improves, it's certainly driven by, the engineering and the technology and the machines that enable us to go to these places. But the most fragile thing in those spacecraft are the people, the humans that are inside. And trying to protect them is a very different question, because if they survive all of the other risks, blowing up, for example, we need to think about what the long-term consequences are. Not only if they're on a planet for a number of years, they could certainly get things like cardiovascular disease or, impaired vision or impaired cognitive abilities or cancer, leukemias, for example, come up, within 4 or 5 years. So are those kinds of things actually going to be affecting our astronauts while they're on a mission? I think is really a very important question. And, what we're going to do about the radiation exposure, we don't have an answer for that.
Yeah.
We just don't, because shielding is such a problem. It's all heavy, concrete, lead, water. It's too heavy to get to launch up there. So we've got to come up with, I think, some better technical answers to those questions.
But I mean, you're describing a fairly well-researched return mission to Mars by astronauts who have as much protection as possible, and they come home within, say, 2 years. But
if they're living there,
SpaceX wants to build a city on Mars, and people go live there forever, right? Like, how little do we know about whether or not that's even a good idea? I mean,
yeah. Well, I would come back, just, my own personal view of that would be come back to radiation exposure. They have to figure that out. I mean, there's just no doubt. I don't think it's that radiation is going to, as we started talking about, mutate everybody or drive evolution. They're going to have to survive it first. And I think that's probably the bigger problem right there.
Yeah. If you could have unlimited budget, yeah,
I like that idea.
It is absolutely my ability to grant as a Canadian.
Okay, thank you.
Yeah, you didn't realize. You think we just build arms, but actually we'll fund any projects you like.
Okay.
What kind of experiments would you like to be able to get at? I mean, we talked about studying them for longer periods here on Earth to see what happens. Maybe include things into the Gateway. What are some big questions, some experiments that you've had rattling around your brain?
Well, I think, we just touched on one, and that certainly would be, the health effects and being able to somehow monitor them for mutations, things, telomeres length, mutations, things that are actually going to affect them while they're on a mission. So improved, medical facilities or improved facilities on whatever craft they're on. They are able now to do sequencing, DNA sequencing on the space station, and they do it very well, in fact. So I think, really building out some of those kinds of things, some of the medical capabilities that they have is going to be really important.
Yeah. One last question here. A.V. Scott and Fly was asking that Scott felt like his legs felt like alien stumps, ankles swollen to a bursting point, terrifying rush of blood to the legs, waves of nausea, pain all over the body. I remember that. I read the book, and
I did too.
He was really miserable when he came back to Earth for a couple of weeks, right?
Yep. Well, he even said that it was 8 to 9 months before he felt normal again.
Yeah.
So I think a lot of that too, that return to gravity is such a traumatic experience. And I mean, there was a very marked and immune response, inflammatory response, all kinds of responses to his return to gravity. And I think that's, you heard talk about, he said, I feel 2 inches taller, or he was. Well, it lasted about a second because the minute everything fell back down, and that's the kind of thing he was feeling. All of the fluids in his body that had shifted upwards when he got on the station because of microgravity suddenly all crashed down too. And it's that process seems to take a little bit longer to get readjusted to gravity than even the one going up and adjusting to microgravity. But evidently his skin felt like it was just on fire. The clothes touching our body or shoes were just, extremely painful.
And that is a year. I mean, can you envision it possibly being lethal?
Well, I don't. I mean, because when he came back, so many of these things did go back at least close to normal.
Yeah.
I don't see it as being lethal in that time period. I think again, if we're thinking though about living on some of these other planets, that's just a totally different thing. But if they want to come back, they have to, there we have a totally different problem than if they stay out there.
Well, it's a fascinating idea to think about, and clearly we need to do more work. We've really only scratched the surface on this, so I look forward to the next science results after my big check arrives and you build your apparatus in space. So we'll get there.
Okay, yeah. It's a deal.
So where can people find out more about what you're working on?
Well, we have, the first manuscript from the twin study just came out in Science last month. So that's certainly a huge resource. It's a humongous manuscript that describes all of the, on a very high level or just an overview level of all of the different results. We're also planning a number of companion manuscripts that will come out hopefully within this year. That describe some of our individual results and also how some of them correlate with each other. So more of that integration between the studies. So I would certainly be on the lookout for that.
All right. Well, Dr. Bailey, thank you so much for taking the time to chat with us today. We really appreciate it, and good luck with your research.
Thank you. It's been a pleasure.
All right. Bye-bye.
Bye. Bye.
All right, let's get on with the rest of the news this week. Kimberly's got more stories. She knows I'm going to go to her first. Kimberly, what have you got for us?
So, if you recall, earlier this year, China landed on the far side of the moon. And we were all super duper excited about that because it was the first time anyone has ever done a soft landing on the far side of the moon. And not only that, but the Chang'e 4 lander landed in one of the most interesting places on the far side of the moon, that being the South Pole Aitken Basin. And the reason that spot in particular is so interesting and why everybody all over the world wants to go there is because it is one of the largest and oldest impact basins in the inner solar system. And in fact, the impact that made this basin was so deep that it probably excavated material from the moon's mantle, which is something that we would never be able to access with a drill here on Earth or anywhere else in the solar system. what the heck is inside planets, we have to wait until something either gouges it out or spews it up. Otherwise, we got no idea. And China landed in one of the few spots where mantle material might actually exist on the surface, where that cute little rover could just pick it up and spectroscopically figure out what the heck's going on inside the moon. And that's exactly what they did. They, for the first time, have spectroscopically analyzed a rock that came from the interior of the moon, which in and of itself is a very cool accomplishment. Never before been done, but we want to do even more of it. But what they found was something not quite expected, as usually happens with research, especially with planets. They never work how you think they're going to work. So what our previous theory was that when the moon formed, at some point it was completely covered by a magma ocean. It was completely molten on the surface, and because of that, a lot of the heavier elements and minerals sort of separated out and fell towards the interior of the moon before it all solidified. So our theory was the inside of the moon should contain a lot of really heavy types of minerals, including some very iron-rich things like pyroxenes and olivines, particularly the olivines. And so when the lander was hoping to look at mantle material, they were looking for things that had lots of olivine in it, because that's what should have been in the interior of the moon. When they picked up one of these mantle rocks, however, there wasn't too much of that particular mineral in that rock, which was a bit of a head scratcher. All the other signs pointed to this rock having once been deep inside the moon, but it didn't have the right mineral composition that we were expecting. But then the rover sort of moved a little bit further away, picked up a different rock, and said, oh, wait, there's the olivine in that rock over there, but not in this first one. What's going on? And so it's giving us an idea that maybe the interior of the moon is either not as rich in this particular heavy mineral as we thought it was, or maybe it's not as well mixed together as we thought it was. Or maybe that first one really wasn't from the interior at all. And who knows? But we got to get some more and figure out what's going on.
I'm going to give credit to the Chinese Space Agency for doing a much better job of letting us space journalists find out about what it is that they're working on.
Yeah,
because
it's the first lander in the coolest place on the moon. And we get to, and they're sharing their discoveries.
They're sharing
with us,
their discoveries publicly.
Happy thing.
So China,
thank you for doing that.
Thank you for doing this.
That.
Yeah, we as space journalists really appreciate it, because I'm sure there's a lot of really fascinating stuff that's going on. And in fact, a lot of stuff. And I'm completely digressing, but I just find like I don't get a chance to see a lot of really interesting research that comes from nations that and research institutions that don't have I don't know as good a public relations department. They have to translate stuff, but I have been finding I'm seeing a lot more stuff coming out of Japan, out of Germany, out of Wales. That doesn't have to be translated so much. That is some of this research, and it's great to see this stuff being put there where we can report on it, because it's really hard for us to know what to report on if not.
And it's not just for us to report on, but it's also for scientists around the world to get access to those data, to run it through their own models, and contribute to answering this particular problem. And you can't really do that if you hoard all of your data and don't tell anybody about it, except in one press release or another. But the paper is available. I think it's in Nature. All the data are available. Anyone with access to it can, try it, using their own, add it to their own data, run it through their own computer simulations of the moon's formation, try and figure out, how this fits in and creates a new picture of what's going on inside the moon.
Yeah. All right. Brian.
Yes.
What have you got for us?
So we don't know how old the universe is.
No, wait a minute. I have it on very good authority that it is 13.8 billion years old. I've been saying that number. Are you calling me a liar?
That's what I was taught in school.
Yes.
We're a bit wrong.
To a first approximation, it's true.
By one method.
So here's the thing: is that we know the universe is expanding, and we know that because the more distant an object is, the faster it appears to be moving away from us. The more its light is redshifted, that type of thing. And so one of the big things in cosmology is to try to figure out what is that rate of expansion. It's known as the Hubble constant. And there are several ways that you can do this. And two of the big ones are looking at how far away galaxies are versus how far the redshift is. So the way you do that is with comparing different stars or supernovas, things like Cepheid variable stars. They pulsate at a very specific rate, and we know how bright they are, so we know how far away they are. You can look at supernova explosions and see the rate at which their brightness is going and calculate this out. So that's kind of the stellar and galactic way of doing this. The other way is that in the early universe, it was this primordial fireball. It was extraordinarily hot. And the remnants of that is the cosmic microwave background. So that leftover heat from the Big Bang, you can look at the background and see how much the universe has expanded and know what that rate is. So the biggest way that we've typically looked at it is with the cosmic microwave background, because the Planck satellite made an extraordinarily good survey of that background and came up with a value for this expansion rate, what's known as the Hubble constant. And they got something on the order of 67 kilometers per second per megaparsec, which means for every megaparsec, or about 3.3 million light years, it's going at 67 kilometers per second faster away. So that's the rate. But the measurements with supernovas and Cepheid variables was a little bit different. It was a little bit higher. And so this has been called the tension in measurements. And normally it's not a huge deal. Normally you would have different ways of measuring scientific values, and every measurement that you make has an uncertainty, so they tend to overlap. So you might have something that's, well, one says 67 plus or minus 4, and another one says 70 plus or minus 2. Well, those uncertainties overlap. So even though they're not the exact same value, they're in agreement. Over time, this has gotten worse. So the latest thing out with the survey of Cepheid variables that Adam Rees did, and he won the Nobel Prize for showing cosmic expansion this way, looked at Cepheid variables and measured the Hubble constant. And he came up with 74 kilometers per second per megaparsec, which is 9% different. So you're talking about a huge difference. But the reason it becomes a challenge is because we know those values extraordinarily well. So the uncertainties now are so much smaller. These values don't overlap. So they're now in contradiction with each other. So you've got basically one method that says the universe is expanding at one rate, and a second method that says it's expanding faster, which would mean that the universe is younger by about 9% or so.
So, but that is like the worst case scenario. I'm trying to think, like if you go right in the middle of those two estimates, is that how you're defining that? Like what if it's the Cepheid variable way, you get one age of the universe, right? And if you go the cosmic microwave background, you get a different number.
Right.
They vary by a billion years.
Those two values vary by about a billion years.
Right. So it is. So and if the cosmic microwave background says precisely 13.8, and the Cepheid variables are now saying almost certainly 12.8, billion years old?
Something like that, yeah.
Okay, great. Have we put these two groups of cosmologists into a room and made them fight?
You just read the journals and you can see this.
You can see the fight, yeah.
You can see the fight.
But I mean, are they getting to the point where they just agree that this is all just madness, and they need to?
So the latest observations of the CFID variables have pretty much resolved that. These two values cannot be reconciled with the models that we use currently. We have been kicking the can down the road with this, where basically the uncertainties were just, you could fudge them enough to say, there's got to be something in the data. There's got to be some systematic error that'll cause them to line up. And they don't line up, and they don't line up by a significant margin. So we now have two different good measurements, extraordinarily good measurements, that do not agree.
So how do we fix this? Is one right and one's wrong? Are they each need to be adjusted by a little bit to meet in the middle? Like,
or did the universe do something weird in between those two times?
See, that's the thing, is that there is a possibility that one set of measurements or another is somehow so skewed by mistakes we just haven't caught that it's just wrong. That, given the size of these projects and given the amount of data that we have, that is almost not possible. I mean, anything's possible in science. We could have people screw up, but when you're talking about hundreds of people working on projects like this, that's not going to happen. But we also can't say, well, just take the average, because taking the average is not supported by either sets of evidence. So we can't just do that and say, well, we've solved it. That's like the old statisticious thing, two hunters go out, one shoots to the left and misses the deer, one shoots to the right and misses the deer, and they look at each other and say, we got him.
Right.
He didn't. Where this probably points to is new physics. There's something about the models that we have that doesn't work. And that's actually really exciting, because one of the things that we've run up with is we're getting so much data that if this actually agreed, that would kind of be sad for science. Because if it agreed, that meant we really do understand everything. And then other stuff that we might not be able to prove, like cosmic inflation, the early inflation of the universe, we may not be able to get the data to distinguish one model from another. And the nice thing about these two different observations is that any model, say with inflation, that can agree with the inflation observations and agree with these contradictory results now has a better chance of being validated. So now there's something else for the theories to grab onto to distinguish one idea from the other.
So what are some examples of weird science explanations, new physics explanations?
So most of them revolve around either some type of modification to dark matter or some type to dark energy. So dark matter has its own problems in that it predicts very well things like galactic clustering on large scales. It even appears to be cold dark matter, but we haven't found any particles to produce this. So in the standard model of particle physics, for example, there is nothing that dark matter could be. So dark matter has to be something else. And so this kind of points to that there may be some other physics. So for example, dark matter may cling to regular matter more strongly than it clings to energy in general, something that would be a variance in relativity, for example. Dark energy is another one. We understand that even less. One of the ideas is that it's just a constant, Einstein's cosmological constant that is built into the fabric of space-time. What if it's not? What if it's something separate from space-time? Or if it's dynamic, there's some evidence that says that it changes over time. We're starting to get that contradiction is actually opening a door for us to figure out what the heck is going on.
Right. I mean, we've mentioned in the past that, that could lead to the idea of the Big Rip. that
Yep.
that the rate of expansion is going to accelerate. The acceleration is going to accelerate over time. But then, I mean, so, we don't have a handle on dark matter. I mean,
No.
that's, like, we don't even know what it is, and now we don't know how much of it there is. Like, that's, whatever. Just like add it to the list of problems, right?
Yeah.
Same thing.
And we don't know how it interacts with regular model very well.
Right. And then the same thing goes with dark energy. Are there other ideas beyond the dark matter and the dark energy?
There are. They're not particularly popular. But I think what's interesting is that we have this kind of puzzle with dark matter and dark energy. We have the mystery of what dark matter is. There are some interesting particle physics results that are kind of hinting at possibly things beyond the standard model. So it's really that we're kind of nibbling at the edges of some new physics. And the exciting thing is that we're finally actually getting real data that we can use to hook onto. It's been, we've speculated about this kind of new physics, but we didn't have any evidence to say this model, not that model. And now that we've got this contradiction between the cosmological constant, the Hubble constant, and some new energy physics stuff, we may have enough data there to start piecing together what this is.
Arjone says, is there any data that we could have in the near future that could resolve this? And also asks, could we get better data if we could see neutrinos from the early universe or gravitational waves from further back in time?
The gravitational wave one is really going to be an interesting one because that provides a whole other set of clues. So as we find more black hole collisions and neutron star collisions, and we get more sensitive at measuring gravitational waves, we'll be able to map the universe in the way that we have with light. So both of these experiments that are contradicting each other now are studies about light, one made by stars and one made by the universe as a whole. Gravitational waves have their own signal channels, that multi-messenger physics. And so as we get more gravitational waves, we're going to have another metric in order to determine the distance to different objects.
And then this idea of neutrinos, right? That there could be some kind of a cosmic neutrino background radiation as well. I know that there's an upgrade to the IceCube instrument down in the South Pole, a 10 cubic kilometer version of IceCube that could theoretically reach a neutrino background radiation. So another...
Right. And there should be a neutrino background radiation. It's just very faint. The interesting thing is that people were hoping that the neutrinos would be able to solve this kind of paradox, that the pinning down the mass of the neutrinos and what that neutrino radiation would be could cause them to line up. Now we know that can't happen. We don't have enough, at least according to what we think of, there isn't enough neutrino background to do that. But it does bring in the idea of how do neutrinos affect these other things? What role do they play? So all of these things are now in flux, and it's kind of exciting.
And back to the gravitational waves, like if the Big Bang Observatory satellite or system gets launched, which is like a super version of LISA or LIGO, that in theory that should be able to actually see gravitational waves from the Big Bang itself. And if they're moving at the speed of light, wouldn't that just solve the problem for you once and for all? We tell you what the universe is?
It could, but the thing is it'll pin down specific things. So the gravitational wave observations would pin down like the age of the universe. But suppose you have an age of the universe that doesn't agree with these two other models. And then you've got three that don't agree.
Yeah. But I guess, I mean, if thanks to the kilonova explosion that gravitational waves and electromagnetic radiation seem to move at precisely the speed of light, you would imagine a gravitational background would probably come in exactly the same as the cosmic microwave background, except off by 300,000 years.
But then you would still have to explain how does the cosmic microwave background shift to give an apparent age from what the gravitational wave age it does. And why do CFID variable distances disagree with both of those or one of those?
So I shouldn't cancel the Big Bang Observer experiment.
No.
Okay.
No.
All right.
Because the more data we have, the thing to keep in mind is that all of these results, all of these constants, are based upon a confluence of different models. So the CFID variable model is based upon relativity, and it's based upon our understanding of CFID variable stars, and it's based upon how we capture that. The Hubble constant from the cosmic and the microwave background is based upon a different cosmological model that has different aspects. So as we get more data, the data is accurate, but the models we have to figure out.
So can you give me a accurate way of describing the age of the universe as I move forward with my popular science videos?
Honestly, 13 to 14 billion years is still an accurate range.
So but I can't say 13.8 billion years. I now have to retreat to we think the universe is around 13-ish billion years old.
13 to 14 billion years. Yeah.
13 to 14.
13-ish is a good thing for that. I mean, this is the other important aspect of this is that, none of this says that the universe isn't inflating, and none of this says that the universe isn't billions of years old. We're just working on those details.
This is a really hard pill to swallow.
This all sounds like job security to me.
I love
Just
it.
saying. I mean,
I work in theory models, so, bring on contradictory data.
All right, Kimberly, you got another story for us.
Yeah, so very quickly. So the solar system is made up of all sorts of elements, including really heavy ones. And even the really heavy ones, things like plutonium, europium, neptunium, all the ones in the song that I forget, those still came from stars too. But which stars is the question. And so we're starting to figure out and where some of the heavier elements come from. And to make a long story short, the answer is that they probably come from the collision between neutron stars and neutron stars. And in particular, for our solar system anyway, most of our plutonium and curium and all those other ones that I'm going to forget, so I'm not going to name them, probably came from one single collision between two neutron stars about 800 million years before the solar system was born. And how we figured that out was looking at the ratios of these different heavy elements from the actinide series of the periodic table, that one of those lines that's actually below the periodic table that they couldn't squeeze in there, looking at the ratios of these different elements in asteroid samples and trying to figure out which of the few ways that we know how to make these elements could have produced these elements in the abundances that we see and in the ratios that we see between different elements. So after crossing off things like a bunch of supernovae, which would have produced way too many of these because they happen pretty frequently on a galactic scale, all things considered, and from regular stellar processes, which don't actually, they produce tiny itsy bitsy amounts, and certainly not enough to seed an entire solar system. The only method that could produce the amount of these actinides that we see in the ratios that we see them in the time scale that we need in order to get them is the collision between two neutron stars. So that's a pretty interesting fact, and it sort of confirms our theories of how these heavy elements are formed through the rapid capture of free neutrons, and that neutron star collisions are a pretty important function in our galaxy.
Again, as I've been saying, that all of the heavier elements came from a supernova. I have to just...
Not all of them.
Not all of them.
Quite a lot of them.
Right, some of them.
But some of them you can only make by smashing a bunch of neutrons at something else.
Yeah.
Really fast and hoping that a lot of them stick. And then you get plutonium.
Yeah.
and
again,
things like that.
like a longer way of describing this
Yeah.
that I'm not pleased about. All right,
Just throw neutrons at it. You'll get new stuff.
So before we go, this is in your honor, Kimberly, and this is a cool paper that just crossed my cyber desk today, and it's just like it just shows the weird universe that we live in now. Some folks from the Max Planck Institute noted that they have found 18 new Earth-sized exoplanets. They announced today 18 new planets the size of the Earth that they had pulled out of the Kepler data thanks to a new technique for studying the light curve as planets pass in front of their parent star. And essentially they had just developed a new algorithm, new technique, and ran it against all of the planets that they already knew about, and then used that to find another 18 Earth-sized worlds orbiting other stars.
Man, that's my favorite defunct mission ever. It is the gift that keeps on giving me planets.
Yeah, it'll never stop. We will still be announcing new planets discovered by Kepler hundreds of years from now.
Yeah, and I think this goes back when Kepler died. I think I said this. We're going to keep hearing about Kepler discoveries as we keep coming up with new and better ways of looking at the data that we already have. There are probably, hundreds to thousands of planets just hiding in there, and their signals are so faint or so subtle compared to the noisiness of stars and spacecraft that we just don't realize that they're there yet. And here's a perfect example of that. 18 new Earth-sized planets around stars that we've already looked at and sort of said, okay, there's one planet there, but no, there's really like 3 or 4.
Yeah.
So
super cool.
Keep going, Kepler. Yay.
Well, while I've got you on my screen, why don't you tell us something interesting that you worked on?
Oh, so as I mentioned last week, I was down in the moon dust looking at a lot of the discoveries that came out of this from the samples that came back from the Apollo mission. And so I spent a whole week learning about all of the nearly 1,000 kilograms of moon stuff that we brought back in the Apollo missions, and what we've learned about lunar geology from that in the past 50 years. So that'll come out in July for the Apollo 11 anniversary. So keep an eye out on that.
I mean, I'm excited, but I am also dreading the 50th anniversary. It is going to be a lot of work.
We're all going to be so overworked, and then August will hit and we'll be like, oh God, what happened? What happened in that month? I don't remember it.
I've already gotten I think
days
like 10 requests to send books for us to consider. So buckle up, everybody. It's
be kind to your space communicators in July. It'll be a rough month.
Yeah, it's going to be crazy. All right, Brian, last but not least, why don't you give us an update on a really cool project that you're working on?
So I've been spending a lot of time recently on a project called Big Science, and it's with a Canadian production team putting together a pitch for a new TV show. We have finished our sizzle reel. If you go to bigscience.ca, you can see a teaser of it, and look forward to it. We are sending it out this summer, and then we'll see, who picks it up.
How exciting.
How do I find the sizzle reel?
It should be on the main page. If it's not, it's on my website too.
Okay.
But if you go to briancoberline.com,
how long is it?
Post.
How long is the sizzle reel?
It's a minute.
Can we watch it?
Yeah, I'm gonna. We won't be able to watch it because people won't be able to. What is going on your website?
Take the first post.
It's like a journal. What?
Yeah, it is.
Have you done?
I've done different things. Go into a static website. It's not WordPress anymore.
Oh, and I can't do full screen. Hold on.
It's on YouTube.
All right, let me try again. You break all the rules here. Okay, hold on.
I don't think YouTube is breaking the rules, Fraser.
No. Okay. Here we
Sorry
go.
to break it to you.
Breaking our rules.
Break it.
Yeah.
Get it?
And I will show my co-host here. All right. They won't be able to hear it, though. Awesome. Please don't give us a copyright strike.
It shouldn't.
Do you promise?
I would be most miffed.
All right, good.
Yeah.
I will let you know when it happens.
Okay. Okay.
All right. Well, we've reached the end of the show. Congratulations on getting that done, Brian. I look forward to the actual show. So this is it. This is the boost that you're going to get.
This is the
We'll
boost.
kick it over the top, and now it's going to absolutely happen.
Okay.
All right. And if people want to go find out more, they can go to briancoberline.com, go to bigscience.ca, find out more. Can people help you somehow, or have they already done that? They helped with the Kickstarter.
Spreading the word is a big thing.
Right. If you're a
That's
Hollywood
the biggest part of
producer,
it. Tell your friends, tell your friends' friends.
yeah, pick Brian.
Yep. That's
Right.
it.
Right on. All right. Well, thanks, everyone. Thanks to our special guest. Thanks to the moderators. Thanks to everyone watching us this week. Thanks to our good friends of the Weekly Space Hangout crew. And Brian, you're going to be with us for a couple of weeks now, right?
That is the plan. Yeah. And
Wonderful.
until late June when I start heading down towards the eclipse.
Perfect. All right. Well, we will see all of you next week.
Okay.